Happy day all. This is Dr. Sridevi from Department of Mathematics. Today, let us see an important, a syllable, but still a simple and an important topic of divergence and curl of a vector field. So, we have so far seen two quantities, which is a scalar and a vector, predominantly used in physics. A scalar is a quantity which just has only the magnitude associated, a measure of how much it varies with it. When you associate a direction, it becomes no more a scalar but a vector quantity. For example, the time, temperature all falls into the category of scalar, whereas acceleration, force, velocity, everything becomes a vector field. Now that you've got a vector field, we will just discuss about how a scalar and a vector are different from each other. When you multiply, add or subtract a scalar, the resultant is always a scalar. But that is not the case in the case of vectors. When you add or multiply vectors, you of course get a vector, but when you go for the multiplication of vectors, you never get the same. It is not always the case that the resultant will be a vector. We have two different products in the case of vector multiplication. Why is that so? We have two quantities associated with every vector, which is a magnitude, and the other deciding quantity is the direction. So depending upon which direction you take in for the multiplication quantity, we have two different vectors there. So once you take a parallel inclination, you get a different kind of a product which will result in a scalar quantity which will give you a divergence, and when you take a perpendicular direction, you get a different quantity called as the curl. So this is what we will be going to see here. Let's see an important operator called as the vector differential operator. So once you have the vector differential operator, which is denoted by the inverted triangle called as the nabla, it is a first order partial derivative operator where it is dependent on the spatial derivative. If in case your field is a three-dimensional field, then you have three directions which is represented by x, y and z, and your nabla contains the three derivatives accordingly, which is dou by dou x, dou by dou y and dou by dou z. If in case it was reduced to two dimension, then of course you will have two things, which is dou by dou x and dou by dou y only. It depends on the dimension, your category of nabla will keep changing. So once you have this operator, we know this is a special operator and it keeps acting on, it can either act on a scalar function or on a vector function also. We have two things when there's a scalar field and a vector field. A scalar field is something where you have the space and each point in that space is associated with a scalar quantity. Whereas in a vector field, in the same space, when you can associate each point with a vector, it becomes a vector field. And this operator can act on both. When it acts on a scalar point function, it can give you a quantity called as the gradient, which is denoted by nabla phi, where phi is the scalar point function. When it acts on a vector field, here comes the difference, whether the way it acts on is according to the parallel direction or the perpendicular direction. When it acts on the parallel direction, you get something called as the divergence, and when it acts on the perpendicular direction, you get something called as the curl. So before going into the divergence and the curl, let's see a little predominant and a prefix of all those things called as the gradient. We know that when the vector differential operator acts upon the scalar point function, you get the gradient, which is denoted by grad phi or the nabla phi, which is giving you this vector. Interestingly, this vector differential operator acting upon a scalar point function gives this gradient, which is in turn a vector. So this is how you denote the vector there. You can see that when your phi is the plane denoted in the diagram below, your gradient phi will be a perpendicular axis to it. So it denotes the rate of change of the force or the quantity that you are going to consider, that is the f or the phi that you are considering, and how it changes according to the space, and this del phi indicates the direction of the fastest rate of change. Imagine when you have a birthday pop and you're popping it. The dust particles scatters across, and when you look at the immediate surroundings, there is a more concentration of the dust particles, whereas when you go longer and longer than the point where you're standing, the concentration of the particles becomes little lower. This scattering is given by the gradient. The concentration gets more, that means the gradient at that point is more. The concentration is less, that means the gradient at that point has a lesser magnitude. Then we now jump into the important topic called as the divergence. We know there are two products, vector products, dependent on the action of the nabla on the force vector or the vector field that we are considering. So once we take a dot product, that is when we consider about the parallel axis, we get the divergence. So once you have the divergence of a scalar point function or the vector point function is given by del dot f, which is given here. It is a three-dimensional vector field, where that is why you have three different derivatives. Interestingly again, these are two vectors acting upon each other to give you a scalar. This divergence is a scalar quantity which tells you the way a fluid expands or contracts. To explain this in a more detailed form, let's consider a flow of a liquid or a flow of a river. In that river, you can see the flow is affected by the landscape lying below it. If you have a pit inside the shore, it seems to that we'll have the change in the flow, and that is indicated by the divergence of it. Depending upon the value of the divergence we get, we can either be a positive or a negative or a zero. We try to classify the rate of the flow of the fluid there. Once you have a positive divergence, we call that to be a source, which is the particle starts to move outside the environment. That is, the outflow of the particle is more. Whereas, when you consider a negative divergence, the inflow is more than the divergence. That is, it is called as a sink. When there is zero, that means the inflow and the outflow are equal to each other, and that is why it is called as a solenoidal vector, and the divergence is zero. It is also called as a conservative field. So once you have this, we can see where it is used now. Let us consider, for example, an electric field. An electric field follows the property of conservation. In any region when you take, the electric field should follow the law of conservation. That is, the particles entering and the particles leaving the field should always be equal. This does not hold for the charged points, where it is a positive charge and a negative charge. When you have a positive charge, you can see that the particles tend to move away from the positive charge. That means it is a positive divergence, which is a source. Whereas when you consider negative charged particle, the particles tend to flow towards it. Therefore, it is called as a sink, and it has a negative divergence. Where is it applied? These are all a few list of the applications which we have, where we try to calculate the magnetic flux of any moving quantity using a divergence, the electric field and the magnetic field, which is given in the diagrams below. The left one is the electric field and the right one is the magnetic field. We try to find out how the scattering happens using the divergence. Also, the heat transfer and the temperature gradient in any transport equation, be it, you will be using the divergence here. You can see as your charged particles behave in your magnetic field, the north pole becomes the source and the south pole becomes the sink. Now jump into the next topic of curl. What is a curl? When you already have a divergence, again that was also a product of the vector differential operator and the vector. Again, this is also it, but what is the difference? The difference there was it was a dot product, now it is a scalar product. That means there it was a parallel axis, here it is a perpendicular axis. So when you consider about the perpendicular axis and you take the product between the same vector differential operator and your vector, the resultant is a vector now. And this is how the vector is being calculated, which is given by curl of S, which is del cross F given by the determinant of that matrix there. So once you have a curl, what is the physical representation of it? Let's look at it. We earlier imagined the flow of a river. Now imagine there is a leaf falling onto the river. Now what happens, depending upon the flow of the river, the leaf starts to move, along with it, it starts to rotate if you have observed. This rotational quantity is given by the curl of it. So a curl is always telling you how the quantity is changing in a rotation, or it tells, in a more physical word, it tells about the vorticity or the circulation per unit area. Let's look at how we categorize the flow based on the curl. Again, it can take a positive value, a negative value, or a zero value. When it takes a positive value, we expect the curl to turn into a counterclockwise, that is, the rotation happens in the anti-clockwise direction. There is a rotation, and that rotation is in anti-clockwise direction. When the curl is a negative, that indicates that the fluid experiences a rotation, but now in a clockwise direction. So when you have a zero curl, it means that there is no local rotation that is happening in the fluid surface. So this is how we categorize based on the value of curl. So once you have it, you can see the below image, which is indicating the population dispersion between two interdependent population. Say for example, a population of a prey and a predator. This is how the mapping is given. You can see that the vectors representing here is following a rotational pattern, which is given by the curl of that vector field. So where it is used, the below image is a common image where you can find in all the newspapers and the news, where it tells you the formation of a cyclone. A cyclone is indeed a vorticity of the air circulation. So when there is a vorticity formulation in the air circulation, you get the curl, and that curl, when it is happening in the anti-clockwise direction, will give you a positive quantity, whereas when it happens in the clockwise direction, it gives you a negative quantity. And that is how you distinguish between the curl happening there. You can also find out how the cyclones forms and what is the direction of the cyclone and where it affects, of course using the curl and its magnitude there. So in order to understand cyclones and in order to understand the airflow when you are traveling through the aircrafts, the airflow will affect the flight, and therefore to study that you can always use the curl of it. So once you use all these things, you know the importance of curls here. Let us take these two diagrams and observe how your curl and the divergence changes according to the flow. You can see the first image, where in the first image, let's concentrate on the center point, which is 0, 0, the center exactly of the figure 1. Let's take that figure and observe what happens to the divergence at that point. You can see that the lines above are trying to converge to that x-axis, and the lines below are also coming upwards towards the x-axis. That means the inflow is higher than the outflow. That means the divergence is going to be negative, and therefore it is a sink. And when you talk about the vorticity there, you can see that there is no vorticity, there is no rotational motion in the figure 1 at the point 0, 0. Therefore, the curl of this point is going to be 0. Let's go to the next figure. So when you look at the center of the figure 2, we can see the number of arrows entering and the number of arrows leaving are almost equivalent in magnitude and in the direction. That means the divergence is going to be 0, therefore it is a conservative or a solenoidal vector there. But it of course follows a rotational motion, therefore it is a negative curl and a solenoidal vector there. This is how you differentiate the curl and the divergence based on the flow of the patterns. So to summarize what you've learned now, we can see the divergence and the curl differentiated within the tabulation. So let's think of the definition where the divergence tells you the spread out of the field, whereas the curl gives you how rotating it is. The resultant, the divergence is a scalar, the curl is a vector. Formula, we have of course a difference because one is the scalar and the other is the vector. The meaning here, the divergence explains the expansion or the contraction of the fluid around that point, whereas the curl tells you how rotative it is. So in order to differentiate one more point we can use, where the divergence, if it is equal to 0, you call that vector to be a solenoidal vector, whereas when the curl is 0, you call that to be an irrotational vector. That means there is no rotation there. As we have learned, I would like to pose a next question to you, where you have to try to find out what are the results of the given following expression. When you take a divergence of a curl, what happens? When you take a curl of a divergence, what happens? First of all, look into if that is possible, and if that is possible, try to evaluate what will be the answer. Thank you.